Good afternoon, everyone, and welcome to this week's edition of our live astronomy show. My name is Justin, one of the astronomers at the Science Museum of Virginia. Happy to be your guide once again. In case you're just joining us for the first time, you're jumping into an ongoing series. We're on our way to the edge of the universe. But we're going one small step at a time, so we won't see everything this week. We have just about wrapped up our time in the solar system. We're going to see a couple more things close to home today, but then we will really be out among the stars. A couple of our usual announcements before we get started. As always, I want to thank our sponsor for the show, Allianz Partners. Happy to have them on board. And this week also need to give a shout out to one of our foundation board members, Elena Edwards, who was just named the CEO of Allianz's U.S. operations. From everyone at the Science Museum, I want to congratulate Elena on this stellar achievement. Also, we'll have links in the comments for you if you are willing and able to help out the museum with our other ongoing missions. Also, for the rest of the show, we're going to be watching video created by our planetarium software. It's the same software we use at the Science Museum in the Dome. It's called Digistar 6. It's produced by a company called Evans and Sutherland. It can do some pretty cool stuff. So I'm actually going to get you switched over to our view of Digistar. We'll get us out into space. Now, if you're able to, I recommend watching this full screen on a nice big monitor, something like that. It'll look best that way. Let's see. Oh, yeah, I had a couple of little minor news updates for you today. I guess still at the bottom of the video, you can see those colorful stripes. You may see those all over the internet today. That is just highlighting the change in global temperatures. So as you look at the globe, realize the climate here is changing. Those are the so-called warming stripes for Virginia. Also wanted to share an important anniversary today. Let's see. I'll have to go back to the big camera to show you that. Today is the anniversary of the launch of the first American woman in space, Sally Ride. So that was here on June 18th, but way back in 1983. So certainly something worth mentioning today as well. It's the anniversary of the first American woman in space. All right, now we are ready to go into space, so let's jump back up there. And you may have already noticed we've got one message in the mailbox. I had one question I saw in the comments last week. Of course, at any point, if you've got questions today, feel free to leave them in the comments. We'll try and address some during the show. We can always come back next week as well. This week's question is from Kathy, who wanted to know, given the enormous distance to the farthest points of the solar system, how is it that the sun holds the smallest and farthest bodies in its gravity, but doesn't pull the closest planets into the sun? Well, that's certainly an interesting question, and I will try to answer it by making an analogy right here at the Earth. So I'm going to add some satellites around our planet here. These are all things that we've launched off of the Earth into space, and you know that the same rules apply because we're working with gravity in both situations. So for satellites that we launch into space, if we don't want them to crash back into the planet, if they stay close to the Earth in low Earth orbit, they've got to orbit around the planet pretty quickly. I've obviously accelerated time here, but those satellites complete their orbits in about 90 minutes. They get a little farther away, and those satellites move a little slower. It takes them much longer to complete their trips around our planet. So it works the same way in the solar system. Those planets closest to the sun just have to move around much faster so that they're completing orbits rather than crashing into the sun. And then farther away, planets move slower. The Kuiper Belt objects go even slower. Those things way out in the Oort cloud that we saw at the end of the show last week go slower still. So that's kind of the amazing thing about gravity. Its reach can be immense. Just gets weaker and weaker the farther out you go. And the same thing happens here at the Earth, of course. There is a certain point where Earth's gravity is no longer the strongest pull you feel. So say if you leave the Earth and you get a certain distance away from our planet, I think I've got a couple more spacecraft out here that can show you what I'm talking about. Look for a couple more big white dots. We'll have some light blue trails sticking out behind them. Let's see. There's one. There's a couple. Yeah, these two spacecraft are just the right distance from the Earth that, well, they've kind of reached the limit of where the Earth's gravity is pulling on them strongest. So they're feeling a pretty substantial pull from the sun as well. Now, they just happen to be stationed at a special point called a Lagrange point where the gravity of the Earth and the sun balances out. But you could imagine a whole sphere around the Earth where the gravity of the Earth and sun balances out, and might look something like this. It's what we call the Hill sphere, if you want to look up some technical terms. But that's just where again, the sun's gravitational pull overtakes the gravitational pull of the Earth. So if you send a spacecraft away from the Earth and you get outside the Hill sphere and you're moving fast enough, you can end up in orbit around the sun instead of the Earth. And of course, that happens from time to time. I have a couple of other spacecraft to show you that are in orbit around the sun. So again, those things with the light blue trails behind them, those are just spacecraft we've launched from the Earth. Now, if you leave the Earth's gravitational control, but then you're going even faster than it takes to get into orbit around the sun, you might escape the sun's control altogether. So we've got a couple of more blue lines stretching way out here, going all the way beyond the planets, beyond the Kuiper Belt where we were last week. And those are the paths of a couple of spacecraft, Voyager 1 and 2, that will eventually escape the sun's gravitational pull altogether. They haven't done it just yet, but they are on their way out. I showed you every single one of those spacecraft for an important reason. Today's show is all about the closest stars. I gave it the title, How Far Are the Stars? And, well, there's no star closer to us than our own sun. The sun is a star not so different from the other stars we can see around us on the screen right now and in the nighttime sky. So I thought we would start by focusing on the sun just a little bit. The Voyager spacecraft, of course, launched to study the outer planets primarily, but now that they're out beyond the planets, some of their instruments are helping us understand how the sun interacts with the space around us. Those spacecraft in orbit around the sun, a little bit closer, are studying our local star as well. Then all of those spacecraft here at the Earth that I showed you, they're all studying the sun in one way or another. Also, some of them are studying the sun directly. Some of them are studying how the sun interacts with the Earth, how material from the sun interacts with our magnetic field, things like that. So every single one of these spacecraft that I put on the screen is part of understanding our closest star. It's a pretty big puzzle to figure out, but it's important to understand the sun, well, because we live so close to it, and our existence is very closely tied to the sun. So what are some of the things that all these spacecraft are teaching us about stars like the sun? Well, I want to start by highlighting one of these spacecraft close to the Earth. Its name is the Solar Dynamics Observatory, or SDO. You can see its position on the screen there. Now, SDO has been up in orbit around the Earth for about a decade now. And it has spent all of those 10 years just staring at the sun. Not a great idea for humans, but SDO is a robotic spacecraft, so specially designed to monitor the sun constantly. It takes pictures very frequently, every few minutes. In fact, I can show you a picture of exactly what the sun looks like right now. Give or take a few minutes. So this is the sun. This is how it would appear to your eyes if it were safe for you to look directly at it. This visible surface of the sun, called the photosphere, is something like 10,000 degrees Fahrenheit. And sometimes, although it's pretty featureless today, it can get darker spots on it. They're slightly cooler regions tied into the sun's complicated magnetic field. We call those sunspots. Now, those sunspots come and go over an 11-year cycle. So over SDO's 10-year mission, it's been able to see pretty much an entire cycle of these sunspots coming and going. And I've got a little video that I'll share with you here. So on the left-hand side of this video is something like what I was just showing you, the photosphere, the visible surface of the sun. You can see a few of those sunspots there. You're also seeing the sun rotate. On the right side of the video, you get a couple of different things. There's a chart there that is graphing how the sunspot number is changing, the number of sunspots on the sun. And then down below is another view of the sun. That's probably more the kind of picture you think of when you imagine a star, right? It's got all these plumes and flares sticking off of it. Well, that's the kind of view you only get if you can see ultraviolet light. That's out beyond the purple end of the rainbow that we can see, but the SDO spacecraft has detectors that are able to see it. So you can kind of pick out also how the activity in the right-hand image, that ultraviolet image, is tied to where the sunspots are on the left. I think all that's pretty cool, but this is a long video, so we're going to remove that from the screen for you. Let me show you another view of the different layers of the sun. So we're looking at the photosphere there, the surface, and then just above that, there's another kind of cool-looking region. This is called the chromosphere. Now, this is a pretty thin layer up above the surface of the sun, but this is where you can start to see some of that activity that we instantly think of when we picture a star in our heads. Then up above that, again, that's what we just saw in that other video, but this is more of a live view at it. And this is a layer of the sun called the corona. Now, that's certainly a word we've been hearing a bit more recently. And the sun has a corona because, well, when it was first seen, you can see it with your eyes during a solar eclipse, it looked like kind of a halo, a wreath encircling where the sun would be. Once astronomers realized it was part of the sun, that they called it the corona. It's just a Latin word that means wreath or crown. So when you hear something like coronavirus, that's actually for the same reason. If you view coronavirus under an electron microscope, it has kind of a halo or a wreath around it too, because of little protrusions on the virus body. But that's not really my area of expertise. Just wanted to give you a little etymology lesson there, a little Latin that you can use in everyday life. All right, so there is the corona of the sun, and SDO can also let us look underneath the sun's surface in a way. It can't see it directly, but I mentioned the sun's magnetic field, and SDO can track that also. This is probably kind of hard to see on your screen, but there are now patches of yellow and green on the sun that matches the polarity of the sun's magnetic field, the different parts of its surface, the north and south poles. So you can already kind of get a picture of how twisted up its magnetic field might be. SDO can also track the motion of material on the sun's surface. It's a plasma. It's like a charged gas. The protons and the neutrons are split apart, and so it behaves in reaction to that magnetic field. And by tracing the motion of the plasma at the sun's surface, you can engage in a study called astroseismology. And just like seismology here on the Earth tracks waves moving through our planet, astroseismology tracks waves moving through the sun. That lets you map the interior structure of the sun. So a lot of information from one spacecraft. But of course, it has help. Those other spacecraft in orbit around the Earth, in space, studying the sun, and also a spacecraft here, telescopes here on the Earth. So let's switch away from SDO's view here, and let's go see what all these spacecraft and telescopes together have revealed about stars like our sun. We're going to jump on over to the sun, take a closer look at it. First thing I will do is make sure we're all aware of what the sun is made out of. I think I've talked about some of the ingredients, the elements that make up some of the planets and other objects in the solar system. So let's check in on the sun real quick. I think I'm going to have to zoom out on this for you a little bit. But we will see that most of the sun is made of hydrogen. It's the most common element in the entire universe. It's the most common element in stars like our sun. Helium comes in second, then a few other trace elements. Basically the same throughout the entire sun. And it's a lot of hydrogen and helium. To give you a sense of scale here, I'll add a couple of planets to the view. We've gotten pretty familiar with those over the last few weeks. So there's Jupiter and even a little tiny Earth off to the left-hand side there to help you get an idea of how big the sun is. So the sun is big. A lot of hydrogen and helium together, mostly hydrogen. And so what's going on under this surface? Well, we can get a little hint by taking a closer look at the surface. We can do that with a brand new telescope here on Earth. The Daniel K. Inouye Solar Telescope is now collecting data about the surface of the sun. Its view of the photosphere looks a little bit different from SDO's because the Inouye telescope can see it in ultra-high resolution. This is real data from the telescope collected at the very end of last year. And just in case you can't read the clock in the bottom right, we're seeing about 10 minutes in a little time-lapse video. As you can see material on the surface of the sun moving. It almost looks like it's boiling. And it's because it kind of is. Heat is carried up to the surface of the sun ultimately by convection. And then that's the same way that heat moves through, say, a pot of boiling water. You're warming up the bottom of the pot. The water at the bottom warms up, rises, releases its energy, and then sinks back down. So you see all these little bright spots here on the sun where material is rising up, releasing light, heat, and energy into the solar system. Then it spreads out and sinks along those darker lines. Just to give you a sense of scale, those convection cells are hundreds of miles wide. Some of them could swallow the state of Texas, so pretty big. If we dive in below the photosphere, we see a region here that I've got just kind of lightly shaded around the outside of the sun. That's where that convection is taking place. But below this convective zone, there's another region which I've got colored kind of an orange color for you. That is where energy travels out from the core via radiation. Now, a radiative transfer is just when you've got the little packet of energy or light. We'll say it's a photon. It's been created in the core of the sun, which you see glowing brightly on the screen through nuclear fusion, hydrogen nuclei crashing together, fusing to eventually make helium. And that releases some photons along the way. Now, in that radiative zone, the photons actually bounce around from particle to particle. The photons don't know where they are going. They don't have any predetermined path to the surface of the sun. So it's estimated that photons can bounce around inside the sun for up to 1 million years. So we asked you in the show post how long it took light from the core of the sun to get out to the Earth, and the round answer is about 1 million years, which I think qualifies as the possibly surprising fact of the day. But we're going to revisit the question in a few minutes. All right, so the light goes from the core, gets out through the radiative zone and the convective zone, leaves the surface of the sun, the photosphere. Where to next? Well, we've seen those outer regions already. Just above the surface is the chromosphere, which I've added, but it's really thin, so it's hard to see. Next up is the corona. And although it doesn't look really huge in those earlier images I showed you from SDO, this is a huge structure. The densest parts of the corona may extend some 18 million miles from the sun, which is something like halfway to the orbit of Mercury. So it's an important part of the sun, and it's an important thing to understand. So we have spacecraft that are studying the corona, and now for the first time we have spacecraft that are actually flying into the corona to study it up close in person. Those spacecraft, one has been in space for a couple of years now. Its name is the Parker Solar Probe. I'm going to put it back on the screen, but it was there for you earlier. We'll see its orbits at some point. There it comes. So you can see how it's diving into the corona there to study that material in place. And there's another newer spacecraft called Solar Orbiter that is going to be studying this region as well. You might also be able to see one new feature of the sun I've added to the screen for you. In addition to these different layers that are relatively well confined, the sun also has charged particles that it sends streaming throughout the solar system. And we call this the solar wind. And the solar wind is really kind of like part of the sun's atmosphere. And so, in a sense, we live in the atmosphere of the sun, and that's part of the reason it's so important to understand our star. The solar wind affects everything in the solar system. It interacts with all the planets. When it interacts with the Earth, because these are charged particles as a plasma, it spirals around the Earth's magnetic field, interacts with our atmosphere, and causes things like the northern lights. Big solar storms can mess with satellite communication, navigation blackouts here on Earth, stuff like that. So we see auroras and interactions with the solar wind on planets and other worlds across the solar system. We've also found, thanks to those Voyager spacecraft, you might see those on the screen again, where the solar wind ends. See, there's this plasma, very thin, charged particles that just fill space between the stars. And those Voyager spacecraft have gotten into that interstellar medium, as it's called. So they've kind of left the sun's atmosphere, but they are still in the solar system because I've also returned to the Oort cloud that we saw last week. So you can see where the sun's magnetic or plasma environment, or where the sun's atmosphere ends. It's much closer to us than where the sun's gravitational control ends. So a lot to learn about our sun and the way that stars interact with any planets they may have. But before we end today, I want to truly get out to some other stars. The sun is important, of course, but it's one of hundreds of billions of stars in our galaxy alone. So if we're going to explore the rest of our galaxy, we should probably know how far we're going to be traveling. So we're just going to zoom back into the solar system for a moment, and we'll talk about how we know how far away the other stars are. It's actually how we know how far away the sun is as well. It's one little trick called parallax. Now, I won't get too deep into what parallax is and how it works. I'll just let you know that it is the way objects will appear to change position against a distant background if you view them from different angles. And I can demonstrate it the same way the New Horizons spacecraft recently did. If I can locate a marker that I've added to the screen for the closest star to our solar system. Let's see. Oh, there it is. A lucky find. All right. So that marker there is showing us the position of a star called Proxima Centauri. And that star is the closest one to the sun. And although we've known the distance to it for a while, and it's most recently been accurately measured by a spacecraft named Gaia, this parallax technique was just demonstrated by the New Horizons spacecraft, something we talked about last week. So I'm going to add the Kuiper belt to the screen there. And back in late April, some astronomers took pictures of Proxima Centauri from the Earth. So that blue line illustrates there. And then at the same time, the New Horizons spacecraft was programmed to take pictures of the same star. Now, New Horizons is currently almost 50 astronomical units from the sun, some 5 billion miles. So it's enough of a distance that New Horizons' perspective has shifted quite a bit. Let's try and get kind of between these lines here. So you can see that the blue one is on the right and the red one is on the left. Now, I'm just going to fly off into space here, and we're actually going to overshoot the position of Proxima Centauri. We're going to go into the background, and we'll see what these pictures reveal. If we actually get into the background, the positions of that star, as seen from Earth and New Horizons, at the same time diverge into different points as well. So here are the real images. This is for that star, Proxima Centauri, the view from New Horizons and Earth. You can see the star appears to jump back and forth relative to the background stars. They did the same experiment with a second star as well. For any Star Trek fans in the audience, this is Wolf 359. Yeah, it's a real star, and it's relatively close by as well, a little farther than Proxima Centauri. So you can actually see that Wolf 359 doesn't jump as far in these two images if you look real carefully, because at a greater distance, that parallax effect isn't as much. So this New Horizons observation was a really neat demonstration of parallax. It wasn't really conducted as a scientific investigation, but that Gaia spacecraft that I mentioned, it has collected these kinds of parallax measurements for over 1 billion stars now, and it's really helped us refine our measurements of how far away the other stars are. That number for Proxima Centauri, just under 4.25 light years, is from the Gaia measurement. Now, I just said kind of a strange word you may not be real familiar with. So one last trip to the solar system. This might really be it. Light year. What's that? Well, that's just a measure of distance that we use a lot in astronomy, especially outside of the solar system. I'm tracking some light here. You may notice sort of a glowing ring around the sun. It's actually some light that left the sun. I'm moving it out through the solar system at light speed. So you can see, although it's moving as fast as possible, it takes a little while to get away from the sun because, well, the solar system is big. Now, if we kept watching here, about 1 minute after we shifted back to the sun, this highlighted ring would get to that first green circle. That is what we could call 1 light minute if we want to measure distance that way. That's kind of useful in the inner solar system. Mercury, on average, a little more than 3 light minutes from the sun. Earth is just over 8 light minutes from the sun. So truly, when you see the sun in the sky, the light entering your eyeballs has been traveling away from the core of the sun for, I don't know, about 1 million years and 8.3 minutes. Then light can keep traveling. Once we get beyond the inner solar system, light hours might be more appropriate. So you can see the distances for the different gas giants. I've got a marker there for 6 light hours out in the Kuiper Belt. That's about where New Horizons is now. It's a little beyond that mark. Our other distant spacecraft have returned to the screen here. And let's see, let's rotate around. We'll get Voyager 1 in the top left for you. So that's our most distant spacecraft from the sun. And it is, since you probably can't read that little tiny label, it's about 149 astronomical units from the sun. Now, in terms of light travel time, that's over 20 hours. So you could say that Voyager 1 is 20.57 light hours from the sun. A lot of times the spacecraft were more concerned with the round trip light time. If we send a radio signal to a spacecraft like Voyager 1, it takes 20.5 hours to get out there. If the spacecraft needs to send a response, then that's another 20.5 hours. So we're looking at over 41 hours for that round trip communication time. But Voyager 1 still within 1 light day of the sun. A light year would then be 365 light days, and 1 light year is probably about the edge of the Oort cloud. Because we haven't been able to directly map that distance, we don't know exactly where it might end, but that's the estimate, about 1 to 2 light years, kind of a fuzzy border. So before I fly too far away, we should add the Oort cloud back to the screen. So if the Oort cloud stretches between 1 and 2 light years from the sun, that means it goes nearly halfway to the nearest star, which I think is also pretty surprising. The sun's gravitational control may stretch halfway to our nearest neighbors in the galaxy. Speaking of our nearest neighbors, we shouldn't end the show before seeing at least one other star. So let's head over to the neighborhood of Proxima Centauri. And perhaps the first thing you'll notice when we arrive are a few lines, because this is a star system. Proxima Centauri is not alone, and that's not unusual. We think in our local part of the galaxy here, as many as a quarter of the stars might have other companions. They might be in star systems, multiple star systems like this. In fact, for the Alpha Centauri system here, we are looking at 3 stars altogether. If we zoom in real quick, on the center of the system, we find 2 stars dubbed Alpha Centauri A and B. So this is a binary pair. They orbit around each other. That's what those lines are highlighting there. And then we've got Proxima Centauri much farther away. To give you an idea of the sizes of the stars here, let's just compare it to our sun, along with Jupiter and Earth, which you've already seen. Alpha Centauri A is the largest star there, and then Alpha Centauri B, a little bit smaller than the sun. They're also slightly different colors than the sun. This might be tough to see on the screen, but the color of a star tells us its temperature. And so the fact that the sun and Alpha Centauri A and B are about the same color means they are about the same temperature. Proxima Centauri, on the other hand, on the far right, more reddish in color. So that tells us it is much, much cooler in temperature. The sun's surface, I told you, is about 10,000 degrees Fahrenheit. Proxima Centauri, about half that temperature. So it's a pretty big difference. Still thousands of degrees, but certainly a shift. Now, let's clear those scales off here. And instead of size scales, let's talk about time scales for a brief moment. These 2 stars, Alpha Centauri A and B, are orbiting around each other. And it takes a few decades for them to complete their cycle, about 80 years. So you're seeing them in motion there. Now, if we back away here a little bit, we will try and get Proxima Centauri back on the screen. And as we move time at this rate, can't really see Proxima appear to move at all on the screen there. Its orbit is so large it takes much longer to complete one orbit. It's been estimated that the orbit of Proxima Centauri around those other 2 stars is on the order of 500,000 years. So if we speed up time a lot more, and it sometimes takes my computer just a few seconds to make this transition, we'll actually see Proxima Centauri start to move along its orbit, and you're also going to see other stars in the background appear to move, just because they are all on their own individual orbits around the galaxy, which is probably something I should explain in the next couple of weeks. So here at the Alpha Centauri system, we've got 3 stars all together, all linked together by their mutual gravity. And there's one more thing that we should see before wrapping up. Let's get a little bit closer to Proxima Centauri itself. Proxima Centauri, despite being a small star, a cool star, it does have a couple planets of its own. We've now confirmed 2 planets in orbit around Proxima Centauri. They are rather uncreatively named Proxima B, the one closer to the star. You're seeing its orbit highlighted there. And then Proxima C, a bit farther away. To give you an idea of the size of these orbits, I'll transport the solar system's planets over here, highlight their orbits on the screen for you. So let's see, 1, 2, 3, 4 orbits would be the orbit of Mars. So Proxima C, about the same distance from Proxima as Mars is from the Sun. And Proxima B, much, much closer to this star. Ooh, crash through it. Don't try that at home. So you might think, this planet much closer to this star than Mercury is to our sun. So it's got to be pretty warm, right? Well, no. Remember, the sun is lower temperature and much cooler, less luminous than our sun. So it is actually at a distance where we think temperatures could be right for liquid water to exist on this planet. We call that the habitable zone. It's the other region highlighted in green around this star. So this planet is at the right distance for liquid water to maybe exist. It would certainly help if this planet were maybe about the same size as the Earth, so that, well, it could be made of rocks and minerals like the Earth, might have a solid surface where liquid water could collect. And, well, if we bring up that scale model of all the objects in the Alpha Centauri system again, and I add those planets to the view, we zoom in here a little bit, we'll be able to see that, all right, so those planets are both much smaller than Proxima Centauri. We would expect that. Proxima b, the one in the habitable zone, is the smaller of those planets. And just to slide the Earth over from our solar system, those two planets are pretty close to the same size. So this might truly be a planet that is the right distance from its star for liquid water to exist. It's the right size to maybe be something like the Earth. So, is this another planet exactly like the Earth? Is it truly a habitable world? We don't really know. There are still a lot of questions that we have to answer, but it's so many questions that I think it would be best to answer them next week. So we are going to, next week, kind of look at a slightly wider view of at least our neighborhood in the galaxy. See what the stars are like all around the sun as a collection of stars, mostly from that Gaia satellite that I mentioned a couple of times earlier. This is a couple thousand stars. They're within, it's about 65 light years of the sun. And one thing to mention here is that a lot of these stars, although some of the color variations on your screen are subtle, they skew a little more towards the red end of that color range I've got here for the stars. So most stars in the galaxy are similar or cooler than the sun. And then, in terms of the planets that they host, we found a couple hundred planets just in this small neighborhood around the sun. You see a couple of other solar systems that have several planets in them. That's what each of those blue circles represents. So many planets out there to explore. Some of them perhaps something like the Earth. So we're really going to dive into the search for these other planets around other stars. We call them exoplanets. And we'll talk about the search for another planet like the Earth next week. Hope you can join me again next Thursday, 2 p.m. Eastern Time. Before we totally get into planets, again, recommend the video that we dropped in the comments about the sun. Don't forget the stars are cool too. But then planets next week. I want to thank you for joining in today. Hope you enjoyed this first step out into the galaxy, and hope to see you next week for more about stars and exoplanets. Until then, be safe out there, and we'll see you next week.